Physics professors at National Taiwan University. It's my great pleasure to chair this session. So first of all, I'd like to introduce our jury. And first is Professor Li Wei from Academic Silicon. Let's give a big hand. The second one, Professor Lin Zifeng from National Taiwan University. Third one, Professor Yao Songwei from National Zhongzhen University. And the final is Professor Liu Chenxiu from National Yang Jiao Tong University. So next, I would like to ask the team captain of the reporter to introduce your members.
Dear judges and fellow competitors, I'm the leader of Team Opposition. I'm Chen Xinwei. 以宋耀贤、徐义佑、洪少凯 and 苏宇安。
Okay, welcome the reporter from Jianguo Junior High School. Okay, welcome. And I'd like to ask the captain of the reviewer. Okay, introduce your members.
Good afternoon, everyone. My name is Winnie Lin. We will from Ningbo High School. The team MD first. This is Wu Junde. This is Li Yunhong. This is Li Yiqi. And this is Lin Hongyan. Good afternoon.
Okay, welcome Jingdao Junior High School. Okay, and the captain opponent, could you introduce your team members?
Okay, I'm the team member, team leader of the team party. I'm Liao Yixiang, and this is Wang Zhijian, Lan Bojun, Chen Dingxiang, Zhi Zhenliu.
Okay, welcome from Jingxin Senior High School. And the observer, captain, could you introduce your team member?
Okay, good afternoon, distinguished competitors and police. And these are the team members. And this is Zheng Yingqi, Xu Yisheng, Hang Shenyou, and Guo Yongjin.
Okay, thank you, the observer. Okay, now we go to the phase one. Okay, the opponent challenged the reporter for the problem.
We want to challenge your ring on the rock.
Which number? Number 3.
Yeah.
Problem number 3.
Reject the challenge.
Reject the challenge. Okay, reject. Okay, reject. Okay, the reporter reject the problem number 3. So opponent, would you challenge the reporter another problem?
Problem 11. Ball on elastic band.
Problem 11 boards on an elastic band.
You accept the challenge.
Okay, the reporter accept the challenge. Problem 11 boards on an elastic band. Okay. So preparation of the reporter 5 minutes. Okay, team, please write down your representative on the whiteboard. Okay, reporter, could you write down your representative on the whiteboard? Opponent.前面那台灯可以关掉吗？可以，不用。最快速度可以。 助教写一下好不好？那个 reshape 刚刚是第3题，然后 challenge 11题。
Good afternoon, honorable judges.
So are you ready?
Yes.
Okay, so now reporter will give a presentation for 12 minutes.
Good afternoon, honorable judges and fellow students. I'm Jonathan Huang from Typt class, and today I'll be presenting problem 11, laws on elastic band. Here's the problem statement. Connect two metal balls with an elastic band and twist the elastic band and pull the balls on the table. The balls will begin to swing in one direction and in the other. Explain this phenomenon and investigate how the behavior of such a pendulum depends on the parameters. So here are 3 important questions to consider. Question 1, which model describes the motion? Question 2, what are the main parameters? And question 3, what's the main cause of energy decay in the system? Here's an overview of our experiment. Now, this is a video of the phenomenon. The 2 balls are connected by an elastic band. The elastic band is then twisted during each period, the band stretches and contracts while the unwinding motion causes the system to swing back and forth periodically. Here's a plot of our graph. The radial system 2 times and the speed v 2 times. And here we can see that both the radial distance and the speed v fluctuates with respect to time. Also, this is the angle of travel by the 2 balls with respect to time. Here's our experimental setup. Our equipment includes steel and plastic balls as shown in the picture to the right. Also, the elastic bands and foam camera and tiles and plastic balls as a surface. And we have a stand and a weight with a hook on it to make a torsional tension. And software we use our tracker and flow sheet for the analysis. The length of the elastic band is measured after we attach it to the 2 balls. And the way we attach it is we connect the elastic band with a lightweight clip as shown in the photo. Now for our theory. This is a diagram of a simplified model of the system. We define the variables phi, beta, and r as shown in the diagram below. So now, there are several factors contributing to energy decay in the system. And first, the rubber band damping, second, radial sliding, third, tangential sliding, and fourth, erosion resistance given by the surface. Energy decay from elastic band. From this graph of the maximum kinetic energy of each period of a torsional pendulum, we can see that the energy decay from the elastic band is insignificant. And the energy decay from radial friction. The coefficient of friction is approximately 10 to the negative 1, while the maximum radial displacement observed is about 3 centimeters. From these data, we can calculate that the energy dissipated in each cycle is approximately 10 to the negative 3. Considering the energy dissipated by the rolling resistance, which we will see in the next slide, this energy decay is insignificant. By marking the balls with white line, we find out that the tangential sliding is small and negligible. Now we consider one turn of the motion. We can conclude that the motion is governed by pure rolling instead of sliding. Now for a model of rolling resistance. First, we have to understand what rolling resistance means and how it affects our system. For soft balls on hard surfaces, rolling resistance happens due to deformations, and while for hard balls, that happens due to collision, as can be seen in diagram B. And the resistance force is given by the following equation, where the coefficient mu sub r is equal to this. And also we can note that the relation is linear in Fedor dot, which is the angular speed of the balls. Here's a theoretical model of our motion. Now we're adding a rolling resistance dissipation term, and we get the differential equation for damped motion. We can solve for this differential equation to get the following, and express the following variables as the following. The system changes direction when Fedor dot changes sign. And recall that from the previous slide, omega d is equal to the following, while b can be expressed in terms of mu k, mg, mgr, and a constant c. The period can be theoretically modeled as the following in terms of the non-physical variables. And as expected of a damped harmonic motion system, the energy decays exponentially, and the kinetic energy can be given by the following equation. Now we will only focus on the decay of the amplitude of the kinetic energy, which is of the form of exponential decay. Now for experimental analyses, measuring the torsion constantly use the torsional tensor, and by measuring the time it takes for each period, we can conclude that the kappa is approximately 5.556 times 10 to the negative 6 per hour probability. And we can also see that the torsional force drives the system into motion by the following experiment. And here's a video of it. For low kappa, the system does not spin at all. While for very large kappa, the system immediately starts to spin, but it also decays much more quickly. And we use tracker to analyze the motion, which we'll see in the following. The amplitude is present as well, and we can see that this fits our prediction. And now for the main prediction, which is the period of the motion. From the following graph, we can see that the theory closely matches the experimental value for both ball 1 and ball 2 of the experiments. And for the last part of our presentation, we will be assessing the different parameters that contribute or affect the period of the system in oscillation. The first parameter we will assess is the period for each cycle. So first we observe about 3 cycles for each chart, and this is on both the floor surface and also on the table. From our experiments of the four different conditions, we can see that each cycle is identical in length. And the initial angular displacement affects on the period. For this experiment, the balls are rotated 70, 100, 120, and 200 times. And we can see that in the graph, the period is constant for different starting angular displacements. And for different mass of the balls, from our theory, we can see that rolling resistance is affected by the mass of the balls. And this is given by the following equation, which we mentioned earlier. And from this, higher mass gives higher damping. And from this, we can predict that higher damping also leads to a larger period T. This can be seen in the diagram to the right. And last of all, we will consider the surface influence on the period. And here's a table of the 4 different surfaces we used for the experiment. And we can see that the number of periods is not present for a styrofoam surface, and this is due to the system does not spin at all on the styrofoam surface. Also, we define roughness with the coefficient of kinetic friction, and it's an easier way to quantify the different parameters. We can see that damping is proportional to roughness in a diagram, and this matches our initial prediction. And here's a video of the balls spinning on styrofoam surface. We can see that the system does not start spinning at all. And also, it's not due to rolling resistance, but instead it's due to the initial torque kappa at sub-zero. And it's smaller than US mgr, which is the torque given by the maximum static friction. Also, we consider the different sources of uncertainty in a system, which can lead to slight deviations in our measurements. And this includes the torsional constant, the pointing effect, and also indices and instability during oscillation. Now, our conclusion includes 5 points and also an assessment of different parameters. The motion can be modeled with a damped oscillator, and the rolling resistance can estimate the energy. The period stays constant for each cycle, and the driving force is the elastic band. Also, there's an upper limit to roughness of the surface, after which the system cannot stop spinning. Element parameters we assess include the following 4 things. The initial angular displacement has no effect on the period, while larger moment of inertia leads to larger period. And also from our experiment, higher roughness leads to larger period, and larger mass causes higher damping, which also leads to larger period. And there are references.
Okay, thank you very much. Upon the next question,
could you please turn your PPT to the page 7?
Page 7.
The left right up corner, right out, how do you mean? What is that?
It's a weight. It's a weight we put on it, and we use it to measure the torsional constant of our elastic band.
So it's a measurement.
We pan it onto a elastic band and measure the motion. And measure the period.
Can we turn to page 5? Okay. What is the V? The V. V is the in the row. V
is the translational speed of the ball. And this diagram is given by a tracker, and it's the translational speed of the ball.
Next, page 27.
27.
Page 32.
Okay, sorry, the time is up. So now go to the stage preparation of the opponent training. Now the opponent takes the floor. 4 minutes.
Okay, now it's my turn to talk about your report presentation. This is problem statement, and the main focus is about the main parameter and the main reason of the energy was paid and the period of the whole motion. The structure of solving the problem is that place the elastic band and put the balls on the table and all again spin in one direction and in another. And the theory is both analysis and Lagrangian. An experimental setup still has the ball and elastic band and one thing to measure the whole rotation. And data analysis is kinetic energy and proportional constant. And the conclusion is that higher mass gives larger damping. System does not start spinning when friction is too big. The motion can be modeled with a damped possibility of initial angular bump effect. And this is pros and cons we think about your reporting. Pros is that your experiment and data is well analyzed at this time. And your comprehensive of your data is very good. And you did prediction with your model and your theory. And you fit to your theory. But with the cons we think about your experiment is that you lack of data. In your chart we only see two points of your experiment and 2 points of your theory. And you
So you want to move to the discussion?
yes.
Okay, so now the discussion between the reporter and the opponent.
The first question we want to ask is that how do you think the energy will transform during the whole process?
So first, the energy is stored as rotation, as potential energy involved, and the potential energy transfers into kinetic energy. All of it both the potential energy from stretching and also the kinetic energy from the system.
Okay. And next question is friction can be modeled, or is it important? And it also connects to the next problem. The mass of the ball is important or not?
About friction, we discussed the effect of friction in our slides. And we found out that both the tangential sliding friction and also the radial sliding friction is too small to be considered when compared to the rotational resistance in the system. So even though friction can be modeled, we do not model friction into our theory. And we don't think it's important when compared to rolling resistance. And also regarding the mass of the ball, we made one of the slides in our parameter section talks about the mass of the ball. And we found that the higher the mass of the ball actually contributes to the larger period of the system oscillation.
Okay, the reporter opponent speak louder. Because we wear the mask. Could you speak louder? Okay, thank you.
So you didn't model the kinetic friction, right?
No.
And but why you show please show your conclusion. You say higher roughness will be larger T, right?
Yes.
So why you didn't measure the kinetic friction, and but you say higher roughness will make larger T.
The kinetic friction coefficient is in this table. And what I mean is that the kinetic friction itself does not contribute to the energy decay of the system. And so it doesn't, and so the rotor resistance is the main reason why energy decays in the system. But the roughness or the coefficient of kinetic friction can contribute to the period in the following way.
But at first your theory make that show that the whole energy will decrease.
Yes.
But why the energy will decrease? It relate to the friction.
Sorry, can you repeat your question?
If the kinetic friction will make the whole energy decay.
No. The kinetic friction, or that comes from any sliding, whether it's tangential or maybe radial sliding, does not affect the energy of the system too much.
Can you show your theoretical model? The one damping, the chart you showed, yes, this one. Why? This show the decrease of the.
That's the amplitude of the oscillation in a diagram. Are you referring to this graph?
What is the y?
Y-axis.
Yes.
That's the displacement or the amplitude of oscillation. And the x-axis is the time.
In your expression, in your chart, we only see 2 or 3 points of your experiment.
Yes.
Do you think that is enough precisely to fit your theory or explain what you predict?
I think it does. I think it does support our final conclusion as you can see that for various different starting initial conditions, the theory, what the theory predicts actually matches the experiment quite nicely. With error rate like 2.3 or 1, maybe 1.06%. And about our lack of data, I think the various kind of data we have can sufficiently support our hypothesis that it's indeed a dense harmonic motion that can describe the motion of the two-bone oscillating system.
I mean, this have in this graph we only have 2, 4, and this didn't fit to your theoretical model.
Yeah, so we consider that we are lacking in data for the discussion of mass's effect on the periods. So you can see that we did not try to fit any line or any graph through these 2 points.
So your conclusion is depend on this and the next graph, or this depend on your theory.
So about mass, and so for the period of mass, we can only predict the way mass and period are related, but not in a quantified way. As you can see in the expression for the damping constant B, there are too many unknowns for the experiment to account for, such as the ratio constant C for the exponential alpha. So for mass and moment of inertia, we did not consider trying to fit our experiment theoretical function against our data.
So in your experiment, do you quantify the rolling resistance?
Do you mean in our model or in our experiment?
Both. Did you try to measure it or try to calculate it?
In our model, we try to quantify the rolling resistance with theory using this slide, and this comes from a paper we read which relates the rolling resistance to the friction, to the rate of collision with the hot surface. But in our experiment, I think we're indeed lacking in data for constants such as the alpha shown here. So for a value of alpha, we rely on the value given by the paper, which is around 1 to 1.5. And also, because the ratio constant C is not determined in our experiment, so we cannot say for sure what the value of the rolling resistance is. But one thing we can say about it is that our model indeed predicts the right period, even though we cannot make sure what the rolling resistance constant is. But it actually is present and is a main influencing factor of our result.
If you try to compare your experimental result and your theory, maybe if you can try to find the C with K is, or try to find the rolling resistance.
We can do that in further experiments to try to quantify maybe the variable C, or to pinpoint on a specific value of alpha instead of just relying on the value given by the data. Yeah, so do that.
So your energy decay is from the rolling resistance.
As we discussed in these slides.
So is the rolling resistance involve the friction or something else? Is that in context what term is it?
The rolling resistance is different from friction in a fundamental way. So as you can see, friction is the sliding or the relative motion between the two surfaces. So like the ball sliding on the surface, and so the force can do work and reduce the energy of the system. But while the rolling resistance is actually not a force but a torque as given by its expression. So the rolling resistance is a torque that comes from a normal force acting against the direction of motion of the system. And for why rolling resistance is present is explained in these two diagrams. And for our experiment, we can explain the source of rolling resistance using this diagram. You can see that the surface is not smooth. And on top of these smooth hills, the ball actually goes from one to the other, causing many different collisions. And in these collisions, the momentum of the system is reduced. So this is the source of rolling resistance in our model.
Okay, now the opponent summarize the discussion. 1 minute.
So at first we discussed about the friction will affect the whole energy decay or not, and the reporter say that friction won't affect the energy decay in significant, won't affect the significant. And next we talk about the rolling. What is rolling resistance? We thought we was talk about the friction or some other parameter or uncertainly variable. But they say that it is about the torque of the lifespan or some on smooth surface.
Okay, thank you. Now the reviewer asks the question to the reporter and the opponent. 3 minutes.
So I want to ask the reporter is when the elastic band and the balls are turning, the string will become shorter, and the friction will deviate from the tangential direction. And how do you think the tangential will move, or where the direction will go?
So as discussed in our presentation, there's actually the tangential and the radial component of the friction. And we concluded that neither of them actually contributes much to the energy decay. But as it contracts, the motion the ball goes in a sideways direction, and it can be decomposed into the tangential and the radial component. So we don't think that it actually affects much the period.
And do you think that changing mass or friction will affect the experiment's results?
Definitely. For larger mass, we think that we propose that larger mass leads to larger periods, and also the rougher the surface also leads to a longer period, and this can be seen in a model for damage motion.
And as for the opponent, I want to ask, why do you think they should model the friction? Or why friction is so important to you?
Because in our experiment, we conduct this experiment very many times, and it will always it always didn't last long for enough to let out to measure. And the reason that the reason that this stuff is mistake is about that the elastic band will hang on the ground, and the next is the kinetic friction.
For the reporter,
I suggest that your experiment you can add like error bars to your chart or like
But yeah.
and there's like one chart in front of your PPT. There's theoretical value and the experiment value that goes in the same train, but there's like obvious arrows there. So
Okay, now we go to the next stage, preparation of the reviewer.
2 minutes.
Okay, now the reviewer takes the floor. 4 minutes.
So we're discussing the topic of false and statement. The problem statements are model describe the motion, parameters, and energy decay reasons. And overall, of reporters, I think they got good time management and proper speed and clear demonstration video and clear research goals. A suggestion, we think that he should explain the train of the chart and why it's going that this train appears that way. And he roughly go through the coefficient K. And in one chart, the theoretical line and experimental line, the train is the same, but he didn't explain the deviation between the two. Once the bigger the angular velocity is, the bigger the friction is, and he didn't explain quite clearly. The overall of the opponent, we think that he also got fluent speaking and good attitude. On the page pros and cons, the words are not clear enough, and somehow they're too concentrate on the flow resistance. The discussion one. The opponent asks is friction model. The theory has mentioned about the whole energy decay, and reported data measure the kinetic friction, and data contributes the energy decay comes from sliding. The rolling resistance is probably relates to kinetic friction, and reporter without rolling resistance can still confirm with the theory too. And too big and negligible, and that's actually important. A discussion 2, opponent just showed 2 or 3 dots in the experimental chart. A reporter thinks that sure the data is precious enough, but sufficiently supports the conclusion. And I think that both a reporter and opponent did a great job on their demonstration. And I think that the reporter needs to give further explain of why the trend goes the same for both numerical value and experimental value, and why does it cause error. And I do think that mass and friction will affect the experiment. And when the ball and the elastic band is turning, the string will become shorter, and friction will definitely deviation from the tangential direction, and the degree will become much bigger than it's supposed to be. Thank you.
Thank you. Now go to the reporter to make a conclusion. 2 minutes.
Okay, so the concluding remark. First, the energy was transformed from the form of torsional potential in the beginning to kinetic energy and stretching potential during each period. Also, we model the motion with depth-harmonic motion, and this can be justified from the nature and the forces acting on the system. Also, we can determine the period accurately from just the change of energy, which we can assess from our tracker analysis. Friction is found to be too small that we can neglect it. Also, we can improve our assessment on the effect of mass in a quantified way. For now, we have that larger mass and rougher surfaces lead to a longer period. And also, our most important model, we consider the model of rolling resistance. And while we do it, we can also use further experiments to pinpoint the values of alpha and constant C. And the rolling resistance comes from the normal force or the collision from the object and the surface. And also answering the question from the reviewer, the tangential and radial component of friction, from our calculations, they do not affect the period that much. And also, for further improvements in our future analyses, we can include error bars in our data plots and our graphs. Thank you.
Okay, thank you. Now the questions from the jury. Any questions? Okay, Professor Lee.
Okay, for the reporter, first my question is, when you treat the torsion coefficient, you use the weight, right, to measure that. But when you do the real experiment, because it twists and the length is changed, so how does this affect the whole experiment?
For one, the length of the rubber band does not actually change too much during the twisting because of the following reasons. First, the twist we do in our experiment isn't too much to cause an obvious change in the length of the rubber band.
Okay, thank you. And what do you think, opponent?
In the measurement of the torsion coefficient, we think it won't affect human too. But we think this phenomenon will affect the whole progress when the for elastic and this system will how they do and training progress will make the our progress can last long.
Okay, thank you. Do you think, do you agree?
Can you please repeat the question again?
Okay, the question is, because the whole experiment, when the two balls, they twist and then the motion starts, I believe the length of the whole band maybe will change a little bit. But when we measure the torsion, the parameter of the torsion coefficient, it's fixed, the length is fixed. So does these two things have any idea that affect this whole experiment?
I think that's when the band changes and the torsion changes as well, because they apparently like the string, the shape of the string, the length of the string changes, and it does affect the torsion.
Okay, thank you.
Thank you.
Any questions from jury? Okay, Professor Lin.
I'm not sure believer. Yeah, so because did you point out any missing point during the discussion? Anything you think may be missing for the discussion as a problem? Would you have any idea or any suggestion that maybe something should be important and they somehow missed?
There's one page, there's the theoretical value and experimental value that goes into the same train, but they did not fit perfectly, or but the error is quite similar. And I think the reporter needs to explain why the errors are so similar, but the train fits together, but it didn't fit.
Any other questions?
So I have a question for the reporters. How do you accurately determine the period by looking at the change of the energy?
So this is actually the most important part of our theory. So you see that according to the electromagnetic model, the energy decays exponentially. So using the energy plot from the tracker, we can determine the exponential b over I. And once we have the exponential b over I, we can calculate this term, which is 2I, which is b over 2I. And this is the main influence, and the omega b determines the period by the relation to pi over omega b. So yeah.
Okay, thank you very much. And now the jury, make a grading. Okay. Now the grading for the reporter. Okay. 6, 6, 7, 5, 7. Now the grading for the opponent. 5, 6, 6, 6, 7. 6, 7. Okay, now the grade for the reviewer. 5, 7, 7, 6, 8. Okay, so now we close the first round. So we take 5 minutes break. So,
You want to challenge your three-sided dice?
problem number 7, 3-sided dice.
We accept the question.
Accept.
We accept it.
Accept. Okay, the opponent accept the challenge. Problem number 7, 3-sided dice. Okay. So now preparation of the reporter, 5 minutes. Each team please write down your representative on the board. Thank you. Okay, now are you ready? Okay, now the reporter give a presentation. 12 minutes.
Honored judges and fellow competitors, today I'm going to report my question number 7 that you guys we are involved. So here's the problem statement. To present a point on the slide is often associated with the idea of a real evidence. What should be the physical and geometrical characteristic of a cylindrical dice so that it has the same probability to be in size and while in space? So our main focus will be find the right characteristic that has the same probability. And the second main focus will be how will different characteristics affect the probability. So here's our outline. So before going into our theory, I want to define what is three-sided dice. So in our experiment, in our theory, we define three-sided dice as a top face and a bottom face, and the adapted area will be the side. So here's our observation. So this is our city observation. we have a 2D observation, so we use a app called Agogo to make the experiment. So before going to the theory, I want to define what is a solid angle. So solid angle omega shown in the picture corresponds to the ratio of the sphere's segment area A and to the square of the sphere's radius R. So here's the equation. So in our first theory, we use the solid angle correspond to any point of the center is given as this. So we decided to use the solid angle to solve this question. So the equation is given by a formula. So because the probability relates on the area of the solid angle will be half phase to side to quadrant phase will be 1 to 1 to 1. So the result of the center project to the solid angle will be the equation below the so there's 4 pi in the front because we type 2 to the equation because there are two phases of the cylindrical dice, and the equation we put in will be the according to the picture in the right. So the center of the dice will be the middle, and to the top phase will be considered as h over 2, and the radius is the top phase radius. So according to our equation, the solid angle will be 4 pi, and in which the probability to top phase to side to quadrant phase will be 1 to 1 to 1. So one of each side's probability will be 1/3. So after having the equation, we decided to use the GeoGebra to find out the ratio of R to H. So we decided to put R as 1 centimeter, 2 centimeters, and 3 centimeters. So the left graph will be the R put in 1 centimeter, and down the H will be 1.79 centimeters in ratio. So here's our second theory. We found that the picture left side will be our second series picture. So we saw that there will be a critical force in the cylindrical dice, so that there will be a line that goes through the center and be vertical to the ground, and because it's vertical, so alpha plus beta will be 90 degrees, and indeed here's the ratio of face up and side to face down will be 1 to 1 to 1. So there's two faces of the cylindrical dice, so we saw the alpha to beta will be 2 to 1, and then the alpha will be 60 degrees and the beta will be 30 degrees. So according to the picture in the right, so we calculate the ratio of radius and height, and we found that the ratio of radius and height will be 1 to 2 through 3 over 3. So here's our experimental setup in 2D motion. So we decided to use Agogo to do the experiment. And this is our experimental setup in 3D. So we decided to use the 3D printer to print out our dice. So the left one is the dice according to our first theory, which the ratio will be 1 to 1.79. The right one will be the one according to our theory, the ratio of radius to height will be 1 to 2, 3 over 3. So here is our variables. So the independent variables will be the ratio of R to H, the radius to the height, and the second independent variables will be the same ratio of the cylindrical dice by bigger radius. What I just said, the radius will be 1 centimeter, 2 centimeters, and 3 centimeters. And the dependent variable is what we want to see will be the probability of living on the space and side. So So here's the result of the ratio of two radius to height and in the 2D form. So in this chart, we can see the times the net interface and interface size. So according to our data, we found that the ratio of 1 to 1.79 fit the problem statement because there's two phases of the size. So we consider the ratio will be 2 to 1 because there's two phases there's two phases in a cylindrical size. So the data in the right will be the ratio of 1 to 2 root 3 over 3. And according to the data, we found that it doesn't match with the problem statement. And then here's the 3D data of the ratio radius to height will be 1 to 1.79. And according to our data and our experiment, we found that the ratio of all these three, the radius of 3 centimeters and 2 centimeters has very close ratio to the problem statement. So it's the ratio of 2 to 1. And the last one, the radius of 1 centimeter, doesn't really fit the problem statement. According to the other two experiments, so we see that this result is much closer to the problem statement. And the third result will be the ratio of radius to height will be 1 to 2 root 3 over 3. And according to this data, we can find that the ratio didn't really fit the problem statement. The ratio of the phase to size will be 1 to 1.56, and indeed this is not what we wanted. So we think that the second CD must have some problem. So here's our discussion. According to the problem statement, we discovered two theoretical models. The first one is the solid angle, and the second one will be the critical point that goes in the center of the device. The first theory led to the result of the ratio R to the radius to height will be 1 to 1.79, and the second theory lead to the result R radius to height will be 1 to 2 root 3 over 3. And obviously there will be one theory will be wrong because there's only one dice that can be the problem statement. So after having experiments with our 2D and 3D mode, the data indicated that the result of the first theory matched better with the problem statement like what I just said. So therefore we believe that our second theory has a possible Persian model. So here's our conclusion. So according to our experiment and our data analysis, we found that the cylindrical dice should have the ratio of radius to height will be 1 to 1.79 that fit the most to the problem statement. And the second one is that both results have the same ratio when the radius is 1. So according to the chart, we can see that both results when radius is 1, there will be a very strong ratio in comparison to the radius equal 3 and radius equal 2. So in this situation, we saw that because the mass of each cylindrical dice have a very different mass because we have a 100% filled dices, so the mass actually has a very large difference. So we think that the mass really affects the probability because the mass is too small and it's harder to let the dice stand up. And that's all. Thank you very much.
Okay, thank you very much. So now the opponent asks the question to the reporter. Opponent, please come here. Thank you.
The first question is that since from your experiment set up, I see that you didn't say the height when you dropped your circuit dice. And did you think it is or not?
So the problem statement was the probability of the phase in its size, so we decided to do it randomly, so you can have the real probability instead of just having the same conditions.
And we can turn to page 10. And why is alpha to beta is 2 to 1?
Because the phase is, there's two phases of the cylindrical diastole, and there's only one side. So we saw that the critical point that goes through the central for critical and the phase, the angle to the phase will be 2 to 1 in the phase of in the size of the angle. The angle from the size to the angle of the phase will be 1 to 2. You read it again. So there's two phases in the central diastole and only one side. So we decided that the probability of phase to side will be 2 to 1. And there's the angle between the phase to the floor and the side to the floor. So we saw that when there's a critical point in the diastole, there's only 2/3 of the probability that will feed to the left and the 1/3 of the probability that will feed to the right. So we think that is 60%.
Okay, thank you. Observation of the opponent. 3 minutes. take the floor. 4 minutes.同学，他那个电的信号不对。
Another kind of connect from the problem is 375. And this is the problem statement. And the main focus is to largest constant probability. And about a theory, they discussed about might be related to the area of the solid angle and simulate the radial of R over D. And thus can you derive the derived model of 375. And about their setup, they didn't explain their setup. So it's hard for me to find the error. And they did clearly point out the parameters that affect the experiment. And about their data is accurately point out their radial and everything about their data. And the advantage is that they have good demonstration video, and they do control the angle analysis. And the suggestion is that they didn't clearly explain how they come up with the radial of R over D. But they have calculated, but didn't mention the motivation. And about their experiment setup, they have used mainly software to analyze the data, but they don't have an individual page about it. So, and about the experiment, the data are also and they did point out the radial, so it's quite accurate. And the suggestions is that in page 18, they didn't mention what did the up chart and down chart means. And so and they need to have a copy of each chart, so we can read it clearly. And we're going to the discussion.
Okay, discussion between the reporter and opponent.
Okay. Since you say that if the ratio is 1.79 and 2√3 over 3 have different results, and how do you see the differences between these two ratios?
So we think that the real difference between these two guys is because the height of the dice will affect our result. When the height is too short, they cannot really flip over to the other base and to the side, so it actually affect our result.
If you think the height will affect, why don't you just make your height stable instead of like just throwing without control your height when you drop?
You mean the initial condition of throwing from the same height?
Yes.
So we think that we didn't throw it in the same height because we want to minimize our results. It's because we want to have the probability, and if we really like make the every initial condition perfect, like you throw from 30 degrees and like from 20 centimeters height, and if you have every initial condition perfectly, and we think that there is no real probability. So,
okay. And about your experiment, you did change the radius between different dices. And how do you think the mass will affect this experiment?
So, according to our experiment, we have the 100% filled 3D printed dices, so the central will get higher and higher within the different radius, because the radius and the height have the same ratio, so when the radius goes bigger, the height will go bigger. So when the central go higher, they affect they affect the result, because when they fall down, if the central is not high enough, they cannot really flip over to the side.
You say that you use 3D printers to print the dice, but how do you determine that the 3D it printed it evenly? Since 3D printer can print thing evenly, so the different point of the two type dice may have different mass.
So we did that here, and we have did a 3D dice only have the 30% field, and when we like print it out, we see the 30% real dice does not really be so decided to use the 100% real dice, so like we can consider the center is in the middle of the dice.
So you do think that the mass will affect the result, right?
Yeah.
And how do you think it will result?
So
Like what parameters will change if you change the mass of the dice?
So according to our CV, there's no mass in our equation, so we didn't really like sort of mass before doing the experiments. But after this, we have some observation and some data analysis. We found that the mass will really affect, but we didn't really calculate how it flips over, when will it flip over in the bigger mass.
Okay, so we do have the same opinion, but and to me, I think the mass will affect the coefficient of restitution. So when the dice drop to the surface, it might drop like bounce up or maybe bounce lower. So this might affect the result. And so
in our experiment, we consider the last rebound of the cylindrical dice, because if we separate every rebound into a part, there will be only one rebound in every part. So we just consider the very last one that will rebound and then you blend it.
and in your experiment, you determine you change the radius of the three-sided dice, but at the same time, you will also change the mass of the three-sided dice. So there will be two parameters, two independent variables in this experiment. So how do you think that your experiment is correct?
So like just said, we didn't really consider math before doing the experiment, so this is our error. So maybe we can have the same different materials to make the dice, so we can have the same mass in the different ratio of the dice. So there will be only one parameter.
And okay. And how about the potential energy? Since if you drop the dice from different height, or if the dice if the contact point of the dice like maybe perhaps is at the edge or on the side, it might affect the potential energy. And how do you think it will affect this experiment?
So we didn't use energy because we saw that the solid angle is enough to solve this question, but like we just said, the energy might affect the result, because when you follow, the energy will transfer into some others integrated energy. So like it might affect the leaving edge of from the floor to the side of the face. So it might affect, but we didn't really actually calculate.
And as you say, you think that if the contact point of the dice may be the edge or the side, why you analysis your data only use 2D instead of 3D?
So the 2D is a simulation of the 3D model. So when you look from one side, the cylindrical dice will be like a rectangular dice. So it's just a simulation of the 3D model. So we usually use the computer to simulate the model. So it's just a simulation.
So if it's a simulation, and how do you think it will work in reality if you did the experiment?
So if you just look from a profile of the side, you will see a rectangular dice. So it's just it might have some real difference in different result in the reality, but it's just a model to show to let us know the real ratio, does it work or does it work.
Okay. And in this PowerPoint, I see there's something right here, and it's seems that it blocked the weight of the dice, and perhaps it would somehow affect the result. Like there's a small like box or I don't know what's that. So when this function, I think it did affect your dice.
Yeah, we did this is the best result, but we didn't actually take it off.
No, I mean that one. The small things when you bounce on it, like this one.
Okay, so this is the last dice the previous result, but we didn't. So in this video, we didn't take it off, but after the result after we already take it off, so it's going like we just take our result.
Okay. And how do you think that how do you think if the material of the surface, like the table in your experiment, will affect this?
So there will be a lot of different conditions in which we have different surface of the table. So in our experiment, we only use the same surface of the table, so that we can ensure that it's in the same condition.
Another question is that you say that the value of the experiment when it's in the radius of 1, it will be a little strange. And did you know the mass of it, like how many grams? Since there might be a critical point between them.
So,
did you measure it?
so the gram will be 4.81 grams. So like because the gram is too small and it's too light, so when it drops to about like a lot of time, so when it comes to a critical point, we have used a camera to measure the critical point. We found that we always land it on its side because the height is not enough and the center is too low that it will flip over to the.
And when the radius is 1, there is a string graduate. And what do you think is the reason? And did you find the maximum point is like there might be a string gradient, and we just find the minimum. But how do you think it will be if you find the maximum point?
What do you mean by maximum?
Like maybe the radius is 6 or 7 or 10.
So like we didn't actually say that. So we only use different sizes. So we only have the smallest value, but we don't know.
And did you explore the characteristic that mentioned in the performance statement? So
our own characteristic is the ratio of the radius to height. Yeah.
So according to the performance statement, it says that they have to have the geometrical one. Did you have that?
So we didn't actually do
Okay, the opponent summarized the discussion. 1 minute.
And okay, during this discussion, the opponent say that they think that the mass wouldn't affect, but when he changed the radius of the dice, the mass and the radius is changing at the same time. So I think it's not a good experiment, like in that case. And also, they didn't consider the surface when the dice drop on, and we did a good job on like discussing on the mass and the everything, and also she should do more on the discussion on 2D and 3D and just remove that block. So this is the end of the point.
The reviewer asks the questions, the reporter, then opponent.
Okay, so my first question is for the reporter. So the problem statement actually asks us to discuss
the characteristics, including the geometrical and physical characteristics. And so, as I saw in your presentation, it was mostly geometrical. Do you have any thoughts on how the physical characteristics of the bare cylindrical device should be?
So the physical characteristic is not we shouldn't do it because we saw that the physical characteristics might affect the probabilities of the energy. There will be some transform of the energy and it might change when the light is like falling to a different edge and
So as I saw in the demonstration video of your presentation, you simply picked up the dice and dropped it without any very uniform method. Do you think the throwing method would affect the results?
So in terms of focusing on the probability, and so we did it in the randomized ways to like get the real probability.
So you believe that there will be no effect of the
Of
throwing?
course, there will be effect, but it's not. It didn't really like. Yeah, it didn't really affect our results.
So you mentioned that your results did not match your second theory. So since this is so, do you think you could possibly adjust your second theory to fit your data?
So after we did the experiment, we found that our second theory had a problem because the line that goes to the center to the slope won't be vertical to the field. So that's why the angle and the ratio is wrong.
I also have a question for the opponent. You mentioned that your data was awesome. Could you elaborate on that a little bit?
Sorry, I just made an error. I think I find the awesome since that they show the ratio between two parameters accurately. But what I have to change is that they have two parameters are changing at the same time. So there are good part and bad part.
So I understand you mean that there should be only one independent variable per experiment. Okay, so thank you guys. The end of our discussion.
Okay, thank you. Now the preparation of the reviewer. In 2 minutes too. Sorry. Now the reviewer takes the floor. 4 minutes.
Okay, so I'm the reviewer today for Typt. Let's first go back to the problem statement. Tonight point on the side is often associated with the idea of a rare occurrence, which would be the physical and geometrical characteristics of a cylindrical dice so that it has the same probability to land on its side and one of its faces. So here's my summary of the reporter's report. First, he explained the phenomena using actual dice rolling, which would be in 3D, as well as a 2D simulation. And for his theory, he used two different theories, and one of them is a solid angle theory, and found that the ratio for the corresponding area of the three faces of a pair of cylindrical dice should be 1 to 1 to 1. And also, the 3D setup was not clearly explained in the report. And for the independent variables, the R to H ratio was changed. And for the same ratio, there were different radiuses that were used. And the dependent variable is obviously the probability of the dice landing on different faces. And so he was able to conclude that, according to his results, pair cylindrical dice had a RH ratio of 1 to 1.79, and that there were strange results when the radius was equal to 100. And next is my summary and commentary of the discussion between the opponent and the reporter. So the opponent asked whether or not the mass would affect the results, and so the reporter answered that mass was not part of the theory, and therefore they could not discuss this very deeply. However, they thought that it would affect the results somewhat. And I think the opponent makes a great point by suggesting that this is another variable that could be considered. And next, the opponent asked for how you could make sure that the 3D printed cylindrical dice was printed evenly. And the reporter answered that while they could not confirm this, the center of gravity should be roughly around the center, and therefore the results would not be too skewed. Also, the opponent asked why a 2D simulation was used, even though the dice had three faces. And the reporter answered that the simulation was simply converted from 3D to 2D in order to be understood more easily. And also, the opponent asked, how do you think the results would differ if the material, if for example the material of the table was changed? And the reporter answered that in order to prevent any deviations, they kept the material of the table constant. And I think this is a great suggestion from the opponent, and also a reasonable answer by the reporter. And so, in my discussion with the opponent and the reporter, I asked whether the reporter thought the throwing method would affect the results, and he answered that yes, but since we are looking for a fair cylindrical dice, then the throwing method should be randomized. And I think it is a good explanation. However, in the future, they can also do some further experimentation to confirm this point. And next are my comments for the opponent and the reporter. For the reporter, I think his advantages are a fluid presentation and compared to the theory to the results, and openly discuss his own errors, and also answer quickly to the questions to save time. And some suggestions I have is to provide some explanation for the 3D setup and to control the throwing method, as well as discuss the physical parameters that the problem statement asks for. And next, for the opponent, I think the advantages are fluid and concise questions, and the suggestions were on point. And there was a clear summary of the report, and I would also suggest the opponent to move on to the next question when the answer of the reporter was clear. Thank you for listening.
So, the reporter make your conclusion. 2 minutes.
Here's our including remarks. So for the 2D, it is the simulation of the 3D model, such as the way that you can see model profile. And the second one is to explain the 2D experiment by showing the mass randomly in the height. And the third one is the cylindrical mass should have the ratio of the radius height is 1 to 1.79. And our both results have the same ratio when the radius is 1, just like the state. Now, next, we still maintain the same release height because we want to make sure the data will be randomized and involved with observed. And then we didn't consider the aspect of energy because we think the solid angle, using the angle has enough to fulfill the problem statement. And that in our future, we will have to ensure that we only have one parameter in every experiment. And that's all.
Okay, thank you. now the question from the jury.
Do you think the acceleration is the solid angle is only one parameter to control the probability? Because if you're taking the same acceleration for the radius and height, if you make the side will become a convex and convex surface, do you think you still get the same result?
Of course, it won't be the same result. Like, it doesn't just that you have a, like, we made a nice to have your center in the middle of the cylindrical band, so we think like, although it may have affected the result, but it won't really like affect the real probability.
So, do you think that the acceleration is the key parameter or any other parameter is missing?
Yeah, that was not the easiest.
I didn't hear this. I didn't.
You didn't get the question? Yeah. And it's very clear that the aspiration of the solid angle is the key parameter. But for the case that you keep the same aspiration for the radius and height, the aspiration is the same. If you make the sidewalk in a convex and concave surface, do you still get the same result? Convex, just convex and concave.
I think it will affect a lot of things like the angular velocity or angular acceleration. So I think the result will be different from what they have done.
Do you think should we get the high probability if you do the convex or concave surface?
I'm sorry.
For the convex, this is how they do the
I think
get the high.
I'm not sure whether or not this would actually affect the results. I believe that the reporter should conduct further experimentation to prove whether or not it actually affected the results.
Professor Lee.
So I think one major problem is this range ratio for particle one or smaller, right? Yeah. So I want to know how you guys think about, what maybe some parameters important to give rise to this kind of deviation. Why, for R smaller than 1, somehow the probability change. Yeah, so maybe you guys can elaborate a little bit more about why this is the case.
So we think that the mass effect, because it's too light to stand up, because the center of the size will be too not so high from the floor, so it cannot really flip over to the side.
I think there should be further explanation on what strange means, because when you change the ratio, there are bound to be extremities in the results, and these are not necessarily strange. They may be the actual natural trend of the probabilities of different cases.
And I think it would be really strange since there might be air drag, and since that the mass of the three-sided dice is very small, and so it would have that. And also, actually, I can read the chart accurately since one of its how they show it is 1 to like 1 to 1 to 2, and another is 4 to 1. So actually, I can read the chart accurately. But if to your question, I think it will also affect the angular velocity, or like if the granule distance between them is changing, and it will also affect. So, yeah.
I think this is an important question because from your model, basically it's geometric. I mean, you should scale up, right, or scale down. But somehow, for smaller size plants, it doesn't work. So I think this is some issue for us. You have to really look into. So mass probably is something you have to consider, or whether this entity, the object, the die, is really uniform density or something, or whether there's a information to drop down on the line, something like that.
Any other questions from the jury? No. Okay. Thank you. So please. So now the jury make a great okay. Okay, now the grading for the reporter 5, 8, 6, 5, 5. Okay. Now the grade for the opponent 5, 7, 6, 6, 6. Now the grade for the reviewer 7, 7, 8, 7, 7. Okay, thank you. So we close the second round and we take 5 minutes break and 7. Problem number 10, structural explosion. Accept, okay. The reporter accepts the problem number 10, structural explosion. Okay, preparation of the reporter action. So reviewer, so could you write down your representative? a presentation. 12 minutes.
Good afternoon, judges. Today's topic we're going to talk about is a droplet explosion, presented by Amy Dropper, and my name is Nicole. So first of all, this is our outline, including the first one, problem statement, the second one, the experimental equipment, the third one is the process, and the fourth one is the theory. And number 5 and number 6, we go back to the initial question we're being asked in the problem statement. And the last one is references. When a drop of a water mixture is deposited on the surface of a hydrophobic liquid, the resulting drop is sometimes fragmented into smaller droplets. Investigate the parameters that affect the fragmentation and the size of finer droplets. And we define the final as after the ring of the smaller ring is completely broken. And here are experimental equipments. From the left, there's a beaker, and there's an electronic balance we use to make the mixture that drips have different concentrations. And here are a syringe, some petri dishes, and colored water with negligible pigments. And we regularly use the sunflower oil as the sublayer liquid. And in the right, the three liquids are defined as the liquid star. Liquid star means that another liquid that matches with water and assemble the water mixture. And the three liquids are all restricted to the liquid that is hydrophilic and lipophilic at the same time. And the conclusion is our induction. So the left one is the isopropanol alcohol, which is the so-called IPA. And the middle one is the amyl alcohol. And the right one is the gamma. And here is our setup. We use 10 microliter per drop. And here is our demonstration video. As you can see here, there's a smaller ring inside, where the color was heavier than the outside. So firstly, we will have to talk about why the spreading will happen. Then we must speak about the spreading coefficient S. The spreading coefficient S is the difference between the work of adhesion and the work of cohesion. So S is equal to work of adhesion minus the work of cohesion. And that can be derived as the S is equal to gamma U minus gamma I minus gamma IU. Gamma I is defined as the surface tension of injected liquid, which is the mixture we drift. And gamma U is the surface tension of underlayer liquid, which is the oil. And the gamma IU is the interfacial tension between the mixture and the oil. And this formula can be rewritten as the S is equal to gamma OA minus gamma NA minus gamma NO. OA is the oil air, NA is the mixture air, NO is the mixture oil. So when S is larger than 0, the spreading will start to happen. So water ring will eventually broken. We can see the transformation from the beginning to the ending of this from this phenomenon. So from the first graphic to the second graphic, you can see that the ring inside will stay the same. And from the second one to the third one, the ring will shrink. And it's kind of like the passive ring deformation. And as you can see, the outward, the bigger circle is keeping increase its area because that the ring is still spreading the little droplets because the S is larger than 0 in the graphic of picture 1 and picture 2. But when in 3 and 4, the ring is keep deforming because the reasons we are going to talk about. So this is the first reason, evaporation. Most of the lipophilic mixture will be evaporated from the ring, which is the thinnest part of the system. The injected droplets will reach a stable condition and will keep decreasing size over time. And for supplemental information, among the liquids, ethanol has the highest evaporation rate, which is 0.15 picogram per minute. But this is still too small for our experiment because we use 10 microliter per ton. And the second one is the dissolution, which we see as a major factor. The bigger the concentration is, the more likely the liquid is going to be dissolved in oil, since the mixture of the oil will have more individual contacts and will thus be dissolved in the oil. And this is an auxiliary phenomenon, which is the Marangoni effect. The Marangoni effect is a liquid with high surface tension pulls more strongly on the liquid with lower surface tension. And this phenomenon will happen with the evaporation and the dissolution at the same time. Because our marine, the surface tension is more close to the water, and that will thus drag the liquid that has lower surface tension inside. So this will make sure the ring is keeping breaking, or you can call it deforming. So here comes our experiment 1. We regularly use the IPA, and the independent variable is a concentration of the mixture, and the dependent variable is the diameter of final droplets. As you can see here, the variable concentration varies from 0.38 to 0.7, and the biggest diameter is 0.146. And in experiment 2, we regularly use the amp panel, and the independent variable is the concentration of the mixture, and the dependent variable is the diameter of final droplets. The value concentration varies from 0.4 to 0.75, and the biggest diameter is 0.315. In experiment 3, we regularly use the ethanol, and the independent variable and the dependent variable is the same. The value concentration varies from 0.75 to 0.93, and the biggest diameter in it is the 0.094. So we've got some speculations for this phenomenon. So the first one, the mixture should reach specific degree of liquid velocity. So the work of adhesion will be larger than the work of cohesion, and the asperity coefficient will be larger than 0. While high concentration can make the mixture lipophilic and thus dissolve immediately when the next. And as we show in below, you can see that when the mass fraction of the liquid start is too low, it will stay. It will not spread. It will stay in the same place. And when the mass fraction of liquid is proper, it will have a flower-like Marangoni wall. And when the mass fraction of liquid is too high, it will immediately dissolve in oil. So our speculation too is that when the concentration is in the range that makes S is larger than 0, the higher it is, the more finely the ring will be shots. And since lipophilic molecules can collide with oil in the ring and dissolve at a higher chance, it means that the final droplets will be smaller. And in the speculation 3, when IPA, the IPA is larger than ampropanol, alcohol, larger than ethanol in a degree of lipophilicity. So the larger the concentration, then the other two is needed if spreading of the ethanol mixture happens. Also, when comparing the diameter of the same concentration of 3 liquids, the diameter of ethanol is larger because it is less lipophilic. So we have classified the possible parameter of height, including 0, 10, 20, 30, and moving on to 100 centimeters. So this is our experiment 4. Regularly use IPA. Independent variable is the height. Dependent variable is the diameter. So when we compare the extreme conditions of 0 centimeter and 100 centimeters, they are almost the same. And this is our relation graph of the diameter of final droplets and different height with dripping mixture into sunflower oil. As you can see, the line, the dots can almost be in a very parallel line. So we think that it doesn't affect that much. So eventually, what are the parameters that the problem statement acts? We think that the first one is a surface tension, and the second one is a type of liquid, which is also affect the degree of the liquid filling, evaporation, and the dissolution rate. And the third one is a type of oil, and that will have influence on surface tension, affect the critical value of spreading, and stop spreading critical value mass fraction. And the fourth one is the concentration of the mixture, which we have proven by the graphics before. And here is the irrelevant parameters, include the height between the mixture. And last one is the unmeasurable parameters. The first one is the temperature. The second one is the atmosphere pressure. The third one is the angle which is the mixture. The first one is the degree of solution mixing. Here are some references. You can see for yourself. Thank you.
Yes. Now the opponent asks the question of the reporter.
Thank you for your presentation. The first is page 18. I noticed that there was a point on page 18. And there seems to be a point that deviates from the trend line. Yeah, I think the point is 0.72.
0.7.
And 0.95. But could you explain what that is?
Because we don't have the enough degree of liquid velocity in the mixture. Yeah.
So, moving on to my next question. Please turn to page 1. Okay. So, could you define what you mean by extreme conditions?
Because the smallest centimeter we cast is 0, and the highest we cast is 100. So these are the extreme conditions that we do in our experiments.
Okay. And the following question is regarding the experiment. So, how did you analyze the droplets? Since you didn't mention what analyze are.
We use a charter. Sorry. Like this. We choose the 3 little drops that seem to be the median and do the average.
Sorry.
We choose 3 of the drops that seem to be like the median and take the average.
Okay, and would you please move on to page 11? You put an illustration back here, and could you explain what the red molecule and
Time is up. Okay, the preparation of the opponent. 3 minutes. Opponent, use the floor. 4 minutes.
Okay, I'm also jumping out of the opposition today. And first, for the summary of the report, the first introduced what kinds of materials to use, which included different types of liquids, including hydrolytic liquids and lipophilic liquids, and alcohol, which was the one that was used most frequently. And for main theories, this explanation for this phenomenon was surface tension. And furthermore, she quantitatively discussed this phenomenon by introducing the spreading coefficient. And furthermore, he also the terms that were in the spreading coefficient, including evaporation and dissolution, which was the main effect. And as he summed up all of the terms within the spreading coefficient, and she explained that this is called the Marinow effect. And to quantitatively explain this phenomenon, she explained that when the spreading coefficient S is greater than 0, then there will be a surface tension gradient, and thus the rim of the droplets will be broken, and thus the Marinow effect can be observed. And for experiment, she used a beaker to drop the droplets, and then used again hydrophilic, lipophilic liquids, and then alcohol. And for the variables in her experiments, first she used different kinds of alcohols, different concentrations of the liquids, and eventually the height of drop, which included the extreme situations where the height of drop was 0 and 100 centimeters. And in my opinion, I think that the reporter did a great job on the presentation, and she also used a great deal of painting skills. And furthermore, in her experiment, she used an ample amount of data, and she also showed that there was a great agreement between her theory and results. And what's even better was that she had a great time control for this presentation. However, I would like to suggest the reporter should provide more demonstration videos and labels for some of the axes in the graph. And now I would like to take a look back at the problem statement and discuss the task fulfillment of the reporter. First, I think that the task of explaining the phenomenon and investigating the effects of plasma droplets was fully investigated. So I think that the report was complete. And however, here are some of the missed points that I would like to discuss with the report. And first, regarding the phenomenon and the theory. And the first one is that, did the surface tension depend on the types of liquid? And regarding the experiment, first, how was the volume of the drop kept constant? Because the reporter only mentioned that she used a beaker to drop the mixtures, and she didn't mention how was the volume of the drop kept constant. And I think it will affect the experiment results, so I would like to discuss on that. And second experiment regarding the experiment was, how was the drop height considered irrelevant? Third, how was the height drop defined? And lastly, what is the time after the rim is broken? And that's all for my opposition. Thank you.
Okay, now let's go to the discussion part.
First question. How was the volume of the drop kept constant? Because one drop, like slightly push the string, and one drop is equal to 10 micrometer, and that's constant. Yeah. So why is the drop height considered irrelevant? Because according to our observation, data tells us that it's almost a parallel line. That can be derived from our data. So,
Yes, but do you have any explanation for that?
we think that is because the viscosity of the oil that's eliminated the kinetic force of the drop.
Okay. So you think that the height of drop didn't affect the experiment results, and it was because of the viscosity of the oil. Okay. Moving on for my next question. You change different types of liquids. Okay. Did you investigate the value of surface tension with these types of liquids?
We have individual surface tensions. As you can see here, but we have difficulty to measure the individual surface tensions. So this is why we cannot calculate as to a very critical value.
Okay. So the reason you mentioned was the reason why there was some points that didn't match the trend.
Didn't match the tracker. You mean which page or
Page 18.
18. That's because, like I mentioned before, that as it's a difference between the work of adhesion and the work of cohesion. And when in a 0.73, the liquid velocity of the mixture is not big enough to make the work of adhesion larger than the work of cohesion.
Okay, I understand. So, for my next question is, what is the time after the rim is broken?
If you want me to answer that, I can answer it, but this is not the main goal we're going to explore in the problem statement. What is the time after rim is broken? I think all of the mixture will dissolve in the oil since we consider the dissolution as a major effect, a major factor that affects this experiment. So eventually it will dissolve in oil.
So, for the next question, the surface tension of ethanol and isopropanol alcohol was similar. Do you agree?
Was similar? No, there are some small differences. And there also have some property differences, but this is not the range of physical properties.
Okay, so you mentioned that the value of surface tension was close, right? But would you take a look at the graphs of these two liquids?
The graphs of these two liquids? Okay. I mean, this experiment is not only about the surface tension, although it really affects, but it's also about the liquid velocity and the
I would like to justify the question that I raised earlier, which was time after the ring is broken. I think that the real question I would like to raise is, what was the time duration between the time? What was the time duration between the broken droplet and the time we record?
You mean from I drop the mixture into what the so-called final appears during the time? We didn't measure that. But after we have already defined what is final, I think the time is not important.
Okay. Then here is another detailed question, which is I think is not quite important to this number, but how did you define the type of drop?
Actually, we use a stupid measurement. We use a ruler, long ruler like 30 cm, 30 cm, 30 cm, and 30 cm. So this is how we used to measure the height.
Also, it is the vertical distance between your finger and the surface of the oil.
It's a cutting edge. Cutting edge is on the ground, and I stand here and drip the mixture. Yeah.
And there, you mentioned that you tested with extreme conditions, and the lowest, the lowest height of drop you used was 0 centimeters. And can you simply explain how did you drop the mixture?
From 0?
Yes.
0 is when the cutting edge is here, and I use a syringe and vertically and very, very close to the surface of the oil and drip it.
Okay. Then, so, so now I would like to ask questions regarding your theory. Now, in your theory, you mentioned that the spreading coefficient, which included the terms of the spreading cause of there were 3 terms I couldn't quite remember, but you mentioned that when S is bigger than 0, then the Merrick-Williams effect occurs.
I have to say that the Merrick-Williams effect happens all the time. Actually, unless there is a high subtension and low subtension. Yeah, it happens all the time.
Okay. So, but in under some conditions, the final drop is contract back.
I think that's because most of the lipophilic molecules all dissolve in the oil, and some even evaporates, so that the cohesion of the water, is probably will affect the kind of like stream, the stream
Yes.
of the yeah. So I think this is what's I mean it's a cohesion of the water that caused this cohesion of water. Yeah.
Okay. We move on to page 8. I'm sorry, I think the page after this. Okay, so again, this is a question regarding definition, and can you define what active injecting means? Passive limited formation?
Maybe I can show you on the blackboard. I think active injecting is when the ring stays in the same place. However, the outer is like this one. It's keep moving bigger and bigger. So this is what caused the active injecting. And the passive ring formation is like, if you can imagine like the ring is like many circles together. And like I mentioned in my presentation, it will finally be chopped. So this is what I think should be called the passive ring deformation, and thus
Okay, so
produce the
for
droplets.
the active injection, there was no deformation of the rings. And
This is a formal time, and this is a time after this is after spreading function reaches 0.
I think that is all.
Now the opponent summarized the discussion.
Okay. In my discussion with the reporter, we first discussed about how the final droplets were analyzed, and the reporter replied that she analyzed the final droplets using tracker. And also, we also discussed about whether or not the differences in surface tension between the different types of oil would affect the experiment results. And the report explained that although some of the surface tension, some of the values of the surface tension of different types of oil were quite close to each other, but however, due to other reasons, there were still differences in experimental results. And furthermore, I asked the reporter for the definition of drop line.
Okay, thank you. Now the reviewer ask a question to the reporter.
Yeah, our first question is, what is your technique to observe the droplet size?
I use my phone.
You use your phone. So, and can the phone see the final size of the droplet since the application will make the final size of the droplet very small? And how could you know from your phone that your observed droplet is not combined by multiple droplets? So that makes it not the final size of the droplet, but it is made by the final size of the droplet.
So your first question is, how can I see normal that this is these small values?
Yeah.
Because after I show the video and I put in the tracker, and I just observe it.
Okay. Now the second question is that do you think that temperature is a great parameter that affects this phenomenon? Since this phenomenon is about the vaporized speed of the alcohol.
You mean the
Temperature of the surrounding gas.
it is very hard for us to control the temperature, but I think yes. But in our experiment, the ratio of the evaporation rates and the volume that we reject is quite small. So in our case, I think that will affect.
So you think that although temperature is a great factor in your experiment, it doesn't affect much. Okay, now move on to the next question.
I didn't say it's a great factor.
Oh.
I didn't say it's a great factor. I said it might affect.
Oh, it might affect. Okay, now, understood. And now the next question is the fragmentation? Is the fragmentation size makes the final droplets the same size?
Same size? Actually, no. That is why I made the error bar.
Yeah. So what is the final size distribution of your experiment? Because as it has different sizes. So is the small one near the rim, or is the small one outer the rim, or what is the distribution of the sizes of the final droplets?
You're asking about the definition?
No, I'm asking about your data.
My data. Okay, so I use a tracker, like I mentioned before, and I choose 3 little drops that seem to be like the median of all the drops, like the median, and I choose the average.
How do you know that it is a medium-sized droplet?
So we do many experiments. So and I even do the error bar. This is because we do many times experiment and analyze many times.
Okay.
So yeah.
Now the next question is when the concentration of your alcohol is great, and how could you still observe the droplets? Since if the concentration is too great, the droplet will be very small. You use the same technique is that use your phone to go to some and use records. Okay.
Okay, now we go to the preparation of the reviewer in 2 minutes. the reviewer takes the floor. 4 minutes.
Hello, judges and distinguished participants. I am the reviewer from team The Question, and in our first, we'll first talk about the reporter. The purpose statement, sorry. And when a thermal water mixture is dissolved in the surface of a hydrocarbon liquid, the resulting drop is sometimes fragmented into small droplets. Investigate the parameters that affect the fragmentation inside the final droplets, or focus on the relevant parameters and their effects on fragmentation of the size in the final droplets. Now, for reporter, the phenomenon they make is by spring deposited mixture on oil. The theory is that spreading parameter evaporation rate. The experiment is different height and different liquid. The conclusion they reach is that the main reason that causes the phenomenon is the surface tension and the liquid that dissolves into the oil. And their strengths are what categorize parameter, characterization, and consider a variety of parameters. Their weaknesses are the volume not controlled by syringe. It's understood from a statement since it is a hydrophobic liquid, the water shouldn't dissolve into it. And next one is the error prone data, since their error bar is too great, as they showed. Next one is the lack of phenomenal explanation, since they didn't explain why the droplet makes dissolving. Clearly mentioned why it is made smaller. Now the next one is the analysis technique needs to be improved. And their bad experimental setup, they failed to control variables like temperature or wind speed or price and something like that. And next one is there is no theoretical model in their report. And about the component, they summarize the broad presentation. They noticed several errors that their workers made, but their weaknesses is they didn't notice it at all and missed a few points to discuss. Now the discussion, upon asked how to keep constant volume, the report says rich, and the reviewer, as I think that to keep the constant volume, it's better to use a height than use a syringe. Next one is why height is irrelevant. The reporter says that from data oil viscosity will reduce the velocity, thus irrelevant. But the reviewer thinks that the height is relevant, and the reason that it is relevant is that when dropping, the alcohol inside the droplet will evaporate into the air so that the concentration will be affected. Next one is, how was the height to be defined? The reporter says long ruler 3 cm, and the reviewer has no comments. Next one is component. What is the time after the reviewer up? The reviewer answered something about dissolve into the oil, but didn't clearly respond to the question, so the reviewer would suggest that the reporter to answer the question more clearly. Now moving on to the point mix. And the first one is the effect of dye in high concentration of alcohol. Since this experiment is about evaporation speed and it is affected by concentration. So if you add dye into it, it might affect the result. Next one is relevant parameters such as temperature, concentration of dye. And the next one is how the volume is this, as I mentioned, is using a syringe. The next one is how to ensure that working is a droplet instead of a string of using the pin. But they didn't use the pin, they used a syringe. But it is the same situation. It's how to ensure that it is a droplet instead of a string, since you push it out of the string. The next one is whether water mixture and hydrocarbon liquids are necessary. And since it needs a lot of time to explain, I'll move on to the next one. And whether different viscosity of hydrocarbon liquid affect the phenomenon, since they didn't quite clearly explain it. And the next one is the flow of the hydrocarbon liquid under the resistors of the hydrocarbon liquid. Thank you.
Give a conclusion.
In my conclusion, I would like to answer about some of the questions I was being asked. So the first one about red dots. It is just the opponent asking. It is just a graphic that shows how the dissolve works. And the next question, why we fail to control the temperature? Because even we control the temperature, it will only ranges from I think maybe 20 to 30. I don't think that is accurate enough. Because I think the reviewer was talking about 0 to 100. So if we range this from 20 to 30, this is only the temperature we can control. So various wouldn't be so evident. And the next question is that why we didn't use pipette, because the syringe is the apparatus that has the smallest scale that we can find in our lives, in our daily lives. Okay, so whether a water mixture and the hydrophobic liquids are necessary? Yes, because it is talked about in a problem statement. Yeah. And whether different responsibility of hydrophobic liquid affect the phenomenon? I think maybe yes, but most of the oil, their viscosity is quite the same. So we have difficulty trying to proven the different viscosity, how will that affect? The flow of hydrophobic liquid under the surface, it could be also very hard to observe at the same time. And because we use the pipette dish, like the thickness is quite small, and it could be made as harder to observe.
Okay, thank you. Now the question from the jury.
So did you mention what is the mechanism to break up the jet to a small droplet? Just like you drink a water bottle, but the tank, there's certain kind of mechanism to break the jet to the droplet.
Sorry, can you say that again?
I mean, can you explain the mechanism? What is the mechanism to break your droplet to a small droplet? Just like your droplet to the mechanism. Yeah, the mechanism. Just like the water pipe, water jet, and a certain kind of mechanism you can break up to many small droplets, right? Yeah, this is for your case, but we didn't mention what is the basic mechanism.
You mean why the small droplet will appear?
How the large droplets split up to many small droplets.
Oh, it's here. Like, if you can see the ring as many circles, and the evaporation and the solution will kind of chop it finely. So in the area here, they'll call the small droplets, and they will induced by the Marinotti effect and go to outside of the rim.
Yeah, Marinotti effect is the force to drive the droplet or the fluid to flow outside, but it doesn't mean the fluid need to break up to many small droplets, right?
The reason why they break up into small droplets is because they're trapped by the evaporation and the dissolution.
This is other kind of can you?
And the same question to the reviewer, what the mechanism?
Mechanism.
Reviewer first, we believe that the mechanism that breaks the droplet into small droplets is a mechanism known as Rayleigh-Plateau instabilities. That is affecting this, that is making the big droplet into smaller droplets.
Yeah, could you explain more what is the Rayleigh-Plateau instability? Which is another different, what factor and what factor, which factor the condition between what kind of factor?
Well, simply put, this phenomenon is like a droplet drops on a hydrophobic liquid, and when it drops, it will spread into a larger surface area. And when it drops into a larger surface area, the central place will be higher, and the rim of the droplet will become thinner. And since it's in the same environment, the evaporation rate of the alcohol should be the same. So now the concentration of the alcohol will be, the center concentration will be higher than the rim's concentration. So due to surface tension, the outer rim will pull the inside droplet into the outer rim, so that it will eventually break. To put it simply.
Can you try to make a connection to the past version?
Please restate your question first.
Yeah. I mean, can you make a connection between the Rayleigh-Plateau instability with the Laplace version?
With the
Laplace version.
Laplace version.
Okay, maybe I asked too much.
Sorry.
Can I say some
find a great question?
I think my opinion is similar to that of the opponent. And since when the mixture is dropped into the center, then if we now ignore the effect of surface tension or other, under normal conditions it spreads. And while it is spreading, and the concentration since the rate of spread of the water mixture is different, and so now we take into consideration the effect of surface tension, and I think this difference of concentration causes differences in surface tension between the molecules. Perhaps I don't have a clear physical concept for that, but I think it is mainly due to reasons of concentration gradient.
Could I explain the question again? Because with the help of our teammates, the reviewers may now answer the question you asked. As I read or now, with house kinetic to themselves is that since it will be pulled to the outer rim, and when it is pulled, the curvature of the central of the thinner area will be greater, and the curvature of the outer area will be smaller. So the surface tension will tend to pull the droplet from the inward to outward.
So the time is up. Okay. Sorry. So now the grading for the jury. Okay, first the grading for the reporter. 6, 6, 7, 6, 7. Now the grading for the opponent. 6, 6, 7, 6, 6. Now the grading for the reviewer. 6, 7, 7, 9, 8. Okay, thank you very much. So we close this stage 3 and take 5 minutes break.
We would like to challenge problem number 2. Very like this.
We accept the challenge.
Accept the challenge. Okay, the recorder accepts the challenge. Problem number 2, grading this.
这个有特征吗？它是一个银色的。哎，那个吗？这个吗？这个吗？哦，知道。这我们班这是我们 report 是类似吗？是。这2万。不好意思，我怎么办？不好意思。我也不知道。那我们前面去，我们前面要不要？
please write down the representative on the blackboard.
知道我们下圈应该告诉你要让我等一下，这个样子，让我帮你。
这个人长会站着，那你小站着比较好。
Okay, so the reporter give a presentation.
Honorable juries and distinguished competitors, my name is Gosu Jiang, and I'm honored to be reporting question number 2, rated disc. The question states that a disc suspended vertically by a thread can be used to measure sound intensity, and the main task is to investigate the accuracy of this device. And first, we can observe how this device operates with the observation video right here. As you can see, the disc deflects significantly after the sound source was turned on. So we can then deduce that with a greater sound intensity, supposedly there should be a greater deflection angle. So by this phenomenon, I conclude 2 key questions for this model. First, what is the relationship between the deflection angle and the sound intensity? Second, what leads to the inaccuracies of this device? So first, this is an overview of this presentation, which includes experiments with different variables, discussion of the results, as well as conclusions. First, for my experiment, the variables includes the radius of the disk r. Second, the incident angle, which I define as the angle that the disk only makes with the propagation direction of the sound wave. And third, the frequency of sound denoted by m. And fourth, the sound intensity level denoted by L sub I. And in addition to a disc suspended vertically at a sound source, I also stick a reflective sticker on the disc and it directed a laser beam to the reflected circuit. So after the laser beam reflects, it projects a dot on the wall. And furthermore, since the laser dot is highly recognizable, so I can use fabric to track the motion of the laser dot after the disk deflects, and therefore I can get the information required that is needed for the analysis. And as you can see, after the disk deflects, the laser dot also moves, so I can get the xt position of this graph. And furthermore, I now consider the relationship between theta and x. So now, after processing, I can convert this data I track into the theta t graphs, which includes information required for further analysis. And for my result, first, I would like to discuss a certain situation with these being the set values. And as you can see, the motion of the disk can be roughly divided into two stages. First, dynamic response. As we can know, for most sound measurement devices, after the sound measurement device receives a signal, then it responses, and after that, a result is output, and we can determine the result from this output. And in this case, the output for the radio disc device is the equilibrium position. However, we can see that the equilibrium is actually not a perfect straight line. And if we magnify one of the segments of this curve, then we can observe that the disk is actually oscillating with a small amplitude. And I fitted this curve with a sine wave, and we can get the information required to analyze the inaccuracies of this device. First, the amplitude of the sound wave is the intensity of perturbation, and this is the main cause for inaccuracy. Furthermore, the 55 right here represents the equilibrium position, which is the output that we're trying to look for. So after this introduction, I would like to analyze the results I got by changing different variables. And first, when the radius of the disk was 2 centimeters, we can see that first the disk experienced dynamic response, but obviously that the disk was not in equilibrium, and so we can get the conclusion that this is an error data. However, by increasing the radius of the disk, we can get a more regular waveform. Dynamic response and equilibrium are all included in this graph. However, if we furthermore increase the radius of the disk into 4 centimeters, we can see that under the same scale of time, the disk only experienced dynamic response. So this means that the sensitivity of time for this device decreases when the radius of the disk increases. And overall, we compare all of the results altogether, we can see that within the time scale of 20 seconds, the optimal radius of this device is 3 centimeters. Next, for the incident angle, I directly plotted the deflection angle, which is the difference between the equilibrium point and the initial position of the laser dot. And we can see a relationship here. And we can observe that roughly around the range of 40 degrees, delta theta reaches its peak around 40 degrees. And this means that this device reaches a maximum sensitivity. Furthermore, we discussed the effect of frequency of sound. Again, when the frequency of sound was 250 Hertz, and with these being the set value for the parameters, we can see that the disk was unstable. But again, if we adjust the frequency that we apply to the device, we can see that, again, a more regular waveform can be observed. So, for the frequency being 450 degrees to 550 degrees, we can observe complete phase transition between the dynamic response and equilibrium. And furthermore, we analyze the deflection angle and the amplitude, which was the intensity of perturbation I mentioned before. We can see that When the frequency of sound is 500 Hz, then the disk experiences minimal perturbation as well as an optimized response. And lastly, the main task right here is to investigate the sound intensity level. So this is the result of measurement, and the x-axis is the sound intensity level, which I forgot to label out, and the y-axis is the deflection angle, delta theta. And again, we try to fit this curve with that formula up there, and we can judge by the value of r squared, and we can see that this is quite a great fit. And now we measure several different values of delta theta, and we compare it to the original graph, which was the theoretical value calculated by this fitting function. Then we can see that the error of the measurements reduces as the sound intensity level increases. And lastly, there is a slight restriction for this device. Since we know that when the deflection angle reaches 90 degrees, then the disk won't be able to turn anymore. So theoretically, the value for delta theta should be less or equal to 90 degrees. And we plot that into the function of ours, then we can get that the maximum value of sound intensity that can be measured by this device is around 84.34 decibel. And in the end, I would like to discuss the possible causes for error of this device. As you can see, in this situation, the sound was not activated. However, we can observe that this still perturbates. And I deduce that this is due to the reason of ambient airflow. Since with the presence of external airflow, it will be able to control, will be able to keep the disk at an equilibrium position. So, for the conclusions of mine, first, we analyzed the T-graph, and theoretically, for a normal radio-based device, the curve should first experience a dynamic response, and then it reaches an equilibrium, which outputs delta theta, and it is the result that we're trying to get. However, in the presence of external airflow, then there will be error data. Second, the causes for inaccuracy or error for this device includes, first, minor perturbations in equilibrium stage, and second, the instability of ambient airflow. And for my next several conclusions, third, the optimal radius of the disk is 3 centimeters when we're talking about the range of sound intensity for my measurements. While the incident angle is around 40 degrees, the device reaches a maximum sensitivity. The range for measuring the sound frequency was around 400 Hz and 500 Hz, and the optimal frequency that can be measured was 500 Hz. That's the conversion formula for the measurement, and can be expressed right here. And that's the restriction of the measurements for this device is right here. And here are the references that contributed to this work. Thank you.
Okay, thank you. Now the opponent asks the question.
I want to ask that if you use the braid to get out the disc,
Yes.
and what kind of braid did you use to do the experiment?
I used a fishing line.
And we know that a braid has a rotation constant. And in the formula you used to relate the theta to the intensity of the sound. Yes. So I want to ask that the rotation constant of the braid, influence the.
I know what you're trying to express. I didn't measure the torsional constant because I thought this wasn't the task that was, this was not the main task that was required by the problem statement. But I do agree that the torsional constant, which is the constant you mentioned, affects the range for the measurements.
And I saw that here have something based on your favorite dish.
Yes.
What is that?
I would explain it verbally. It was a reflective circuit. It is something sort of like a mirror, and when a laser beam hits the reflective circuit, then the laser beam reflects. Is this one you were talking about?
Okay, thank you. So now the preparation of the opponent. Opponent take the floor. Over to you.
Now I want to discuss the problem to related. This problem is to find the accuracy of the accuracy of the method that use relatives to measure the intensity of the sound. And in your experiment, you use the theory that the relationship between the theta and and the intensity of the sound. And your setup use measure this and the surface that can make a diffraction from the laser. And also you use the dot that on the ball and reporter use the dot on the ball to calculate the theta of the angle of the disc and so reporter can calculate the intensity. There are some methods of reporter provided in basic explanation. Clear graphs explaining the phenomenon. Compares different parameters. Well-structured report. Summary is clear. And there are also some weaknesses. Not enough theory to back up experiment results. Does not thoroughly explain the phenomenon. Parameters unchanged. Problematic experiment. Here are some questions I want to discuss with you. First, what is the result that causes this divergence? And the relation between sound intensity and accuracy. And what is the frequency influence the result? And we know that the disc is easy to be interrupted when we put it in a large space. So what do you do what does reporter do to prevent this happen?
Okay, now we move to the discussion. Reporter.
The first question, what is the result that causes the disc diverge?
I think it is the suppose that this is the disc, and then the sound source is right here. Then the air that flows around actually does something like this. And I think that the reason why the disc deflects was due to the reason that on the two ends of the disc, the air pressure at the two ends of the disc were high. This zone of high pressure makes the disc tilt.
And what makes the high pressure?
Excuse me?
The high pressure was caused by what factor?
I think I don't have a clear concept for the physical mechanism behind this, but in some of the references I read out, we can now, since sound waves in air propagates as transverse waves, so it actually goes back and forth. And this is the interesting part because the disc actually stops at an equilibrium point. instead of oscillating with the air particles. And the reason for that is, I think that the two velocities on the disk actually forms sort of like a couple. And due to this couple, the disk rotates and stops at an equilibrium position because once the disk is rotated, then the thread that suspends the disk, because the torque that is exerted by the thread also increases. So as the disk rotates, the torque exerted by the thread also increases, and thus an equilibrium is reached.
I want to ask you a question about this diagram. So in your explanation, when the sound go like this way and the disc will rotate counterclockwise. What do you do to avoid the disc from being interrupted from the unknown factor?
I think this is a great question. I tried to cover up the whole setup using a cardboard box, but I think that this reduces the inconvenience in experiment operation. So I think this is the main reason. But I think covering the whole setup with a cardboard box could possibly reduce the effect of external variables.
Do you think choosing a disc that is easy to make a diffraction from the sound can increase the accuracy?
Excuse me?
Do you think that choosing a disc that is easy to make a diffraction from the sound can increase the accuracy?
I think sound wave itself is already easy to diffract, since the wavelength of sound waves are usually, for example, 50 centimeters to 1 centimeter. But then, if we're talking about frequencies such as 250 hertz or something like that, so I think that I think you mean that changing the radius of the disk could change how easy the sound diffracts. But I think that it wouldn't have much of an effect because the wavelength of sound itself is already great enough.
We know that the diffraction of the sound will hurt the situation of the air around the disc, and also
excuse me, I think diffraction is not the main cause for this deflection. The line I draw right here represents the line with the same pressure, and because due to the differences in the air pressure, then the disc rotates.
If we put another sound source in another place, you think that the sound created by another sound source will affect the pressure on the disc?
And yes, I think it would have an effect.
So I think diffraction is also the same way like put another sound source.
Yes, I agree.
So the diffraction should change the pressure on this.
So you're trying to express that different sound source changes how sound diffracts around the disc, right?
But this is not similar to the thing you say that the diffraction event doesn't affect the phenomenon.
I think in the situation you mentioned, it does affect the diffraction, but I still don't think it is a main factor because, as I said, the effect of diffraction of sound waves is already common. So I think it changes the effect of diffraction, but I don't think the effect is significant. And I would like to answer several questions on the slide right here. And I think that what may cause the oscillation during the equilibrium? I think that it is due to the situation that there are imperfections in the thread, so that sometimes the disc rotates back to its equilibrium point, and however, it is sort of like a simple harmonic motion in some sense. When the disc rotates back to its equilibrium position, the angular acceleration at this point is 0. But however, the angular velocity right here is not 0, so it goes to the other direction, and then the process repeats.
You say that this will go back and causes this oscillation, but the disc will put back. You think that the disc will go back is because the version of the rate or another factor?
I don't think there are any other factors. I think it is the main reason for the oscillation. And since the time is going to do so, furthermore, I think the mass will have an effect on the moment of inertia of the disk, so I think it would affect. And furthermore, the thickness of the disk should theoretically have effects on the phenomenon. Thank you.
Okay, the opponent summarized the discussion. 1 minute.
The method they use, the reporter used to measure the intensity, they measure the angle by with the dot on roll. I think this way is. I think this is a good way. This can prevent that if you observe the motion of the disk, it will be another discrepancy.
Okay, thank you. Now the reviewer come here, ask the questions to the reporter and opponent.
Why does the intensity of the perturbation represent the accuracy of the device?
Because in ideal situations, the disk should first experience an oscillation with its amplitude decay. Then, in ideal situations, it completely stops at an equilibrium point. However, due to the minor perturbations, and which means that it still oscillates. So,
And for the Why do you think, can you explain why the dispersion is an important factor?
Because diffractions may change the screen around the disk, and the screen exchange, it will cause that the pressure on the disk change.
Okay, thank you. And for the recorder, how do you adjust the frequency of the sound in your experience?
The sound source I used was of adjustable frequency, so I can directly adjust the frequency of sound on that device. And the reading right here represents the frequency of sound.
And if you test the frequency smaller than 455 and bigger than 555.
For frequencies under 255 Hz, I think that I wouldn't put it in this presentation because it would lead to the same results as the one with 250 Hz. And as for frequencies bigger than 550 Hz, I didn't conduct further experiments on that.
Okay, thank you. And that's my question.
Okay, thank you. Now the preparation of the reviewer committee. Now the reviewer takes the floor.
Hello everyone, I am the reviewer of D101. And this is the overview of the reporter's presentation. First, we didn't see any theory in their presentation. And the setup is about the track the movement of the laser dots. And they did the fixed radius from 2 to 4 centimeters. And they did 450 kilometers and 550 And they have the maximum self intensity by 83.4. And the first will be false. And their optical frequency will be 500. And this on public payment. This solution can be monitored there to safety and capacity. This device can be used to measure the intensity sound by turning on the transistor. Effectively, the capacity of such a device. And this controls resistance and adjustment improvement. They did enough of experiment to have their and they can improve they have a little bit of error in their experiment and they make need a better video to show on their demonstration. And the opponent and very several opponents to be discussed. And there are some factors about some reasons. And the discussion. The point is like the opponent is about what do you do to avoid the next being interrupted? And the reporter says that they block all the experiments that can possibly avoid it. And the opponent asks, using a lot of this that can be easy enough to reflection. And the opponent responds, some way already easy enough to reflect. And we agree with that. And the problem is different sources affect the depression. And the reporter says it will, but it will not be the main factor. And our opinion is that might not be the main factor because it won't affect that much. And another point raised by the woman is there any factors that will affect the oscillation? And the reporter responds, the mass may affect. And we personally think that it affects the movement of the disk, which is important. And our question is to the woman, what do you think the reflection will make it better? And the woman says the reflection will cause movement of hair moving. And salting. And our another question is, how do the reporter adjust the frequency of the cell? And they say they use phone to adjust it. And the recent point is the material of the stick.
Thank you. Time is up. And the reporter gives the conclusion.
Okay. I would like to thank both the opponent and the reviewer for raising very important questions. And first, I would like to thank the opponent for raising an interesting physical insight, which states that the diffraction of sound may also lead to a difference in the deflection of the disk, which I consider to be negligible. And second, I think the reviewer also raised very good questions, and such as the materials of the disk and other questions. However, there are several points that I would like to justify. So, first, the frequency of sound was adjusted by the device that I have used. So, I think there should be no concerns regarding this part of the experiment. And after the discussion, I think it is truly appreciable that I obtain more possible variables for my future experiments, including using threads with different torsional constants and changing the length of the thread, which also affects the torsional constant theoretically. And third, changing the thickness of the disk and see what differences will be observed. And fourth, using different sound sources, which was a suggestion that I came from the opponent, who suggested that different sound sources may give to differences in the diffraction of the sound. And I think that's all for my concluding remarks. Thank you.
Okay, thank you. So now the question from the jury.
So, yeah, for the reporter, you mentioned that there's a frequency. Yes, I'm curious about what affecting this why this optimum frequency 500 hertz. Maybe for other people also comment on this. Are you fully convinced that there is a really optimum frequency for this type of detection technique? So why 500 hertz was the best?
I actually don't have the explanation to that. But judging from the viewpoint of physics, the frequency affects the wavelength of the sound wave. So I think that this effect might be related to the wavelength of the sound. So yeah, but still I don't have a definite answer for
why there's optimum frequency? What do you think about this conclusion of this optimum frequency 500 hertz? What's your opinion here about this? Are you convinced of this frequency?
I think maybe the range can be tried to vary from 50 because maybe up to that.
For the opponent, I have seen another formula that used to describe the work on the LEDs. It is looks like this.
Or maybe you can say what determines the optimum frequency, or what key rise to this 500 hertz? What factor?
According to this formula, it used that diagram to prove the formula, and in higher frequencies, that the velocity of the sound will change faster than the lower frequencies, and in this case, we can assume that the motion of the flow is unchanged because it is fast and slow. So the work on the disc will not be that constant. So I think this is why also the 500 hertz not the best situation to do the experiment.
Another question from some question comes from your concept. The doctor mentioned that the sound wave just right. So you agree with that, and you agree with that?
I actually forgot whether it was longitudinal or it should be longitudinal, which is.
You can see it.
A sound wave is longitudinal or that's great.
I think it's supposed to be.
So you opponent general question is that sound wave is transverse or longitudinal.
We can change this question. We can read that this is transverse. And how about you?
I didn't understand the question.
Let me ask one more question. Did you try different the size of speaker? See if it affect the movement of the disc. Different size. No. All right.
Okay, thank you very much. The time is up. The jury make a grading. May please see. Okay, now the grading for the recorder. 6, 6, 7, 5, 5. Now the grading for the opponent. 5, 6, 6, 5, 6. Okay. Now the grading for the reviewer. 5, 6, 6, 6, 5. Okay, so we are going to end stage 4. Thank you everyone's effort. Okay, please take a good rest tonight and we'll see you tomorrow.